Hi, I'm Prof and welcome to Chemistry Matters, and today we are going to be talking electrochemistry. Right, a little bit of trivia for you to kick off with today. The oldest person ever to win the Nobel Prize in Chemistry was 97 years old, I believe, when he won that. And his name was John B. Goodenough. What a great name. And he won the Nobel Prize essentially for the development of the lithium-ion battery. And as we all know, we could not do without our lithium-ion batteries nowadays. They have pretty much changed the world. Batteries used to be big, old, clunky things. Now they're tiny and they power all of your mobile devices, your laptops, your phones, etc., etc. So his discovery essentially changed the world. Lithium-ion batteries. Batteries are examples of, or very practical examples, I guess, of today's topic, electrochemistry. Okay. Now, as the name suggests, electro, you can think of electrons. And so this is the chemistry of electrons, essentially. Electrochemistry, it's all about the transfer of electrons. Now, we have touched on this already when we talked about balancing redox equations. Now, if you cast your mind back, redox equations, remember, that is a combination of two words, reduction and oxidation. And again, think back, reduction is a gain of electrons and oxidation is a loss of electrons. And so any reaction that involves essentially one species giving up electrons to another species is a redox reaction, okay? And it's, in other words, an electrochemical reaction. Now, we go back again in history, way back to sort of the late 1700s, and a guy by the name of Luigi Galvani, who you're probably not surprised to learn was Italian, and he was playing around with dead frogs for some reason, and he was using electrical energy to make dead frogs' legs twitch. Okay. And this was essentially the start of electrochemistry, believe it or not, or of humans studying electrochemistry, because electrochemistry has been around since the dawn of time. But it's only really in the past couple of hundred years that we've grown to understand this. Okay, and he sort of correctly figured that, okay, so, well, sort of correctly figured, let's say, that this electricity, this newfangled electricity, had some purpose in the body, and we certainly know that that is now the case, okay? And so what about electrochemistry? What's important about it? Well, again, if you've watched the videos on thermodynamics, you'll remember that we defined this thing called Gibbs energy. And Gibbs energy essentially told you whether or not a particular reaction was going to be spontaneous, and essentially how much energy you could get out of that spontaneous reaction. Now, electrochemistry is intimately associated with Gibbs energy through this nice simple equation, delta G standard is equal to minus N F E standard. Okay, and that is probably an equation that you should learn, I guess, if you are in a class where they don't give you an equation sheet for your exams. And so this is directly relating delta G standard, thermodynamic quantity, to E standard, which we haven't met it yet, but it's the electromotive force of an electrochemical cell. In other words, a voltage, essentially. N is the number of electrons that are transferred in your particular electrochemical reaction. F is a thing called Faraday's constant, and the value of that would always be given to you. But the important thing about this equation is it's linking delta G standard and E standard. Okay, so what are the practical applications of this, of electrochemistry? Well, well, as we've already seen, lithium-ion batteries, massive practical application. But if we go back again in time and we do an experiment, we take a rod of zinc and we dip it in a solution containing copper 2+ ions, okay? And what do we see? If we leave that zinc rod in that solution, what we would then see is that over time, we would get a copper metal coating on that zinc rod. And so what would be happening is that we would be dissolving some of the zinc and we would be forming solid copper, okay? And that's kind of cool. So that gives you a way of plating, for example, copper onto a zinc surface, okay? Now, the interesting thing is that if we do this in reverse, what happens? In other words, if we take a copper rod, a rod of pure copper, and immerse it in a solution containing zinc ions, zinc 2+ ions, what happens? And the answer is a big fat nothing, okay? So we've got a process that is spontaneous in one direction, but not the other. Okay, and you know we've talked about this in the whole thermodynamics side of things. So what's going on here? Well, hopefully from what you've learned about balancing redox equations, you can see that the zinc is going from zinc 0 to zinc 2+. So in other words, it's losing 2 electrons, and so that therefore is an oxidation process. And then the other half of things, you've got copper 2+ going to copper metal. And so in other words, the copper 2+ is gaining those 2 electrons that zinc is losing, and we've got a reduction process happening here. So we're getting reduction. So zinc is getting oxidized, copper is getting reduced, and essentially what is happening is that the zinc is giving up. It's losing 2 electrons that are being used by the copper 2+ to get reduced to copper metal. Okay, so that's all well and good. That's just essentially a straightforward redox equation that we are going to balance. But you might ask the question, just how much does zinc want to lose those 2 electrons? And just how much does copper 2+ want to gain those 2 electrons? Is there any way that we can sort of quantify this? Is zinc very prone to oxidation? Is copper 2+ very prone to reduction? Or is this a difficult reaction to get going? Or does it just occur very, very, very spontaneously? And, you know, so how do we figure that out? How do we put numbers essentially on all of this? And the answer is that we use a thing called a galvanic cell. Or we can use a thing called a galvanic cell, let's say, okay? And so we can set up these in the laboratory and we can measure essentially the voltage of the electrochemical cell that's corresponding to this particular redox reaction, okay? So remember the redox reaction, the overall redox reaction is solid zinc plus copper 2+ aqueous going to solid copper plus zinc 2+ aqueous. Okay, that's our overall equation that is occurring in this thing here, which is called an electrochemical cell. Okay, so let's have a look at this because it's really, really important that you understand exactly what's going on here because sadly, electrochemistry is the cause of much pain and suffering amongst students, again, in my experience. So let's make up what we're going to call an electrochemical cell, or what is sometimes called a galvanic cell, after our friend Luigi Galvani, who was mucking around with the frog's legs. Okay, so what have we got here? We have got a rod of solid zinc, and that is immersed in a solution that contains zinc 2+ ions, okay? We have got a solid rod of copper, and that is immersed also in a solution that contains copper 2+ ions. Okay, now what we are going to do is we are going to connect the solid rod of zinc and the solid rod of copper using a conducting wire. And we're going to put a voltmeter in the middle of that as well, okay? Because we want to measure the voltage. We want to measure how easy it is for this particular reaction to occur. Now, that's all well and good, except nothing will happen until we put in this thing here, a salt bridge, okay? So a salt bridge is essentially, as the name suggests, a bridge between these two aqueous solutions, okay? And this contains, surprise, surprise, a salt. And that is necessary for things to happen because, as we will see, we have to maintain the charge balance between these two solutions. Otherwise, nothing's going to happen. Right. So we've got all set up, ready to go. Let's connect the terminals and put our salt bridge in. What happens? Well, we can kind of figure out what should happen because we already know that if we take solid zinc in the presence of copper 2+, we know that the zinc gets oxidized to zinc 2+. We know that the copper 2+ gets reduced to copper. So the zinc is very happy to lose electrons. The copper 2+ is very happy to gain those electrons. And so what we find is that when we connect this all up and get it ready to go, that electrons start spontaneously flowing from the zinc electrode through our voltmeter, which measures electron flow, and to our copper solid rod of copper here, okay? And so they are going to now accumulate on that solid rod of copper. We're going to have electrons on here, and the copper 2+ is going to gobble up those electrons and turn into solid copper. Meanwhile, the zinc is busy giving up those 2 electrons, and it's turning into zinc 2+. In other words, it's dissolving. So if we left this going and going and going, essentially this solid rod of zinc would dissolve away completely, okay? Now, we've got some terminology, and it's terminology I don't particularly like, but this is what it is, so you're stuck with it. So this is stuff to commit to memory, unfortunately. Okay, now, think about it. The electrons are flowing from this side here to this side here. In other words, they're going from the left-hand electrode. That's what we're going to call the solid rod of zinc now. We're going to call it an electrode. And we're going to call our solid rod of copper, we're going to call that an electrode as well. And when we put our voltmeter in there, we find that current is flowing. Okay, we have a potential difference between this electrode and this electrode, the zinc electrode and the copper electrode. And when you have a potential difference, what happens? You get a flow of electrons, you get electric current, which is a flow of electrons. And that's what's happening. The zinc is giving up electrons and they're flowing through here. And the copper 2+ is gaining those electrons. Okay? So in other words, remember electrons have got a negative charge. What are they going to flow towards? They are going to flow towards something that has a positive charge, aren't they? That's the way electric current works. Electric current flows from something that is negative to something that is positive. So therefore that must mean in this electrochemical cell that this rod of zinc formally has a negative charge. So this is a negatively charged electrode. We give it a special name. We call it the anode. Okay? Anode, negative charge, anion. Okay, remember anions are negatively charged, an anode is negatively charged. And the electrons flow from the negatively charged anode to the positively charged, and this will be no surprise, cathode. Cation, positively charged, cathode, positively charged. Okay? And that's what's happening spontaneously in this electrochemical cell. The electrons are flowing, and the electrons are flowing only in one direction. Electrons do not flow from the copper cathode to the zinc anode. They do not do that spontaneously. Okay, so electrons flow in one direction and one direction only. Now, what's the purpose of the salt bridge? The purpose of the salt bridge, as I mentioned briefly before, is to keep electrical neutrality in these two solutions. Because remember, what's going on in these two solutions? Here, you're forming zinc 2+ ions. And you can't just form positive ions without having negative ions to balance the charge. And so therefore, the salt bridge has got cations and anions in it, and so anions will be flowing into the solution to balance the formation of zinc 2+, okay? And conversely, what's happening in this solution? Well, remember, the electrons are flowing this way, the copper 2+ ions are being used up and are plating onto the cathode here as copper. So you're losing cations in this solution. We don't want that to happen, and so therefore the salt bridge will be providing cations into this solution to replace those that are being used up in the electrochemical cell. And that's why you need the salt bridge in order for any electron flow to occur. You take out the salt bridge, all the electron flow will stop because of the fact that you cannot keep electrical neutrality in these two solutions in that case, okay? Right, so we've said that that is our spontaneous, or our direction of spontaneous electron flow. Then let's put it into chemical equations. What's happening at the right-hand electrode is that copper 2+ is reacting with 2 electrons that come from that electron flow to give solid copper. And you know from the redox video that that is a reduction, okay? And conversely, what's happening here? You've got solid zinc. Solid zinc is losing 2 electrons. It's turning into zinc 2+, and so therefore losing electrons is an oxidation process, and so we've got oxidation occurring here. And that is true for any spontaneous electrochemical or galvanic cell, is that reduction occurs at the cathode and that oxidation occurs at the anode. And that's really, really, really important. That's one thing to absolutely remember. For a spontaneous electrochemical cell, reduction occurs at the cathode, reduction with a C in it, cathode. That's one way to remember, C, cathode reduction, oxidation at the anode, okay? Right, so that is the absolute fundamentals of electrochemical cells, and we will talk more about electrochemistry in the next video, okay? So we will see you then.